Okay, let's just get right into it. We are all using these incredibly powerful AI tools now, right? From chatbots to code assistants, they're everywhere. But behind all that magic, there's this hidden cost, a performance problem that kind of affects all of us.
And you've definitely felt it yourself. You type something into a chatbot and you wait and you wait. That lag, that little spinning wheel, it's not in your head. Serving up these gigantic AI models is a huge, huge computational challenge. So what's really going on under the hood?
To really put this into perspective, let's talk hardware for a second. A single, top-of-the-line NVIDIA A100 GPU, this is a beast of a chip. It can only handle less than one single request per second when it's running a pretty standard 13 billion parameter model. Let that sink in. Less than one request per second. If you're trying to run a real service for lots of people, that is a massive, massive bottleneck.
To understand why it's so slow, we have to talk about memory, because it turns out the biggest problem isn't really the raw processing power. It's all about how these models use this one very specific, very precious resource, GPU memory. So check this out. On a 40 gigabyte A100 GPU, the model itself, its parameters, takes up about 65% of the memory. Makes sense. But look at that huge orange slice right next to it. A full 30% is being eaten up by something called the KV cache, and that is our culprit.
So what in the world is this KV cache? Well, think of it like the model's short-term memory. To figure out the next word in a sentence, the model needs to remember all the words that came before it. The KV cache is where it stores that context, all the attention keys and values, so it doesn't have to recalculate everything from scratch for every single new word. It's totally essential for speed, but man, it just devours gigabytes of memory for every single person using it.
And here's where the real problem kicks in. The traditional way of doing things requires that the KV cache for each user needs one big, unbroken chunk of GPU memory. So if the system can't find a continuous block that's big enough, all that memory just goes to waste, even if there are smaller empty spaces scattered all over the place. It's kind of like trying to park a huge semi-truck in a parking lot that only has a bunch of small single spots open. It just doesn't work, and you end up with a ton of wasted space.
So we've got this huge, inefficient memory problem. But what if there was a smarter way to manage it? Well, this is where a breakthrough serving engine called vLLM comes into the picture. And it honestly just changes the whole game.
vLLM is this awesome open-source library that's built to make running these big models fast and easy. And its secret sauce, the thing that makes it so special, is a brand new algorithm they developed called PagedAttention. It's designed to attack that memory fragmentation problem head-on. And you can really see the difference side by side here. On the left, you've got the old way, these big, clunky, wasteful blocks of memory. But on the right, you see vLLM's PagedAttention. It's so much smarter. It breaks the KV cache up into these smaller, fixed-sized chunks they call pages, and it can slot them in wherever there's free space. No more continuous block needed, no more wasted memory.
Now, if this idea sounds a little familiar to any of you with a computer science background, well, it should. The researchers behind vLLM took their inspiration directly from one of the most fundamental concepts in modern operating systems, virtual memory and paging. It's basically the same brilliant technique your laptop uses to manage its own RAM, but now it's been applied to the world of AI.
Okay, so the theory is fantastic, right? It sounds great on paper. But what does this actually mean in the real world? Let's look at the performance numbers.
This right here is the headline figure. A recent study found that, on average, vLLM gets 6.47 times higher throughput than the standard method from Hugging Face. And get this, that's on the exact same hardware. We're not talking about a small improvement here. This is a massive, massive leap in efficiency.
And when we break it down by model, the numbers get even crazier. For CodeLlama 13b, it's a 5x improvement. For the bigger CodeLlama 34b, it jumps to 8.5x. Look at the super popular Mixtral model. We're talking over 14 times the throughput. And for some of these models, the results are, well, they're just staggering. Take a look at this. It's almost comical. For the Wizard Coder 33b model, the standard way of doing things just crawls along at 1.6 tokens per second. But with vLLM, that number just skyrockets to almost 44 tokens per second. That's a 27 times performance gain just from changing the software. It's incredible.
And as if PagedAttention wasn't enough, vLLM has another trick up its sleeve called continuous batching. So instead of waiting for the slowest person in a group to finish their request, vLLM just immediately starts working on new requests the second a little bit of space opens up. This keeps the GPU busy all the time, which pushes utilization way up and boosts throughput even more.
Now this kind of crazy efficiency, it opens up a really fascinating new door. What if you didn't need those super expensive, always sold out GPUs anymore? What if you could run powerful AI on the hardware you probably already have?
No, that's exactly what's starting to happen. The optimizations in vLLM are so good that they're making high-performance AI a real possibility on standard everyday enterprise CPUs. This could totally change the game for who can actually afford to deploy and run these models.
A recent white paper from Red Hat and Intel actually put this to the test, and they found that the newest generation of Intel Xeon CPUs running vLLM could support 1.88 times more simultaneous users than the previous generation while keeping the exact same response time.
The benefits here are just huge. I mean, we're talking lower costs because you're not fighting for GPUs. We're talking about the ability to scale up your AI using the commodity hardware that tons of companies already have in their data centers. And you know what? It can even mean better energy efficiency, since CPUs often use less power than those big GPUs.
As the white paper itself concludes, this combination of vLLM on CPUs offers a compelling alternative. It's really about democratizing access to powerful AI and pulling it out of the exclusive realm of specialized, crazy expensive hardware.
So the big takeaway here is this. By solving a really fundamental problem with memory, technologies like vLLM aren't just making AI faster. No, they're making it more accessible, more affordable, and way more scalable than it's ever been before. And that leaves us with a really exciting question. If the barrier to entry for powerful AI just keeps getting lower and lower, what amazing new things are we all going to build next?